Okay, this is a very basic circuit that we're going to look at. We're just going to run a few tests just to try and verify the relationship between a live signal and the signal drawn on the oscilloscope. Okay, what I want to show here is just a little experiment, time series signals and real time, how they reflect on the oscilloscope. I've got two LEDs down the bottom there, a green one and a red one. You can see the red one flashes at the bottom of the peak and green one at the top. Now on the oscilloscope we've got a y-axis which indicates the amplitude of the wave, normally a voltage amplitude. And we have an x-axis which indicates the time. Now you can see here in time the wave is being written to the screen from left to right, and you can see as the wave's being written to the screen that the LEDs flash. So you can see got a peak, 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 and with each one of those peaks coincides the LED flashing. Okay, so what's written here on the screen at this time, moving from right to left, all this data over here is old data that's been stored, okay, and it's being overwritten as we go through. Now the chunk of data there, if we stop it, that chunk of data there is what's being stored in the buffer, in the memory, digital storage oscilloscope. This is what's being stored in the storage, and you can see that real time. You zoom in, zoom out, all that sort of thing. Okay, so what we're seeing here is we're seeing real live wave being written from left to right, which coincides with the flashing of the LEDs. So we've got a trough, peak, trough, peak, and each time we hit one of those peaks, trough or a peak, we see a flash real time on the LED. Okay, we can see here we've got an applied voltage, a current, and then a back EMF, and our positive amplitude and our negative amplitude on our Y scale, and time again is on our X scale. Now what they're telling us here is that the voltage leads the current by 90 degrees. Okay, so if we were to come down on our time scale and we slowly move along, move along, move along, move along, move along, and we have a voltage at 90 degrees, it's at 0. Or inversely, if we were to do it at the peak, we say, right, at the peak we've got a maximum voltage, and if we move along, move along, move along at 90 degrees, we then have a current maximum. So the voltage were to lead the current. However, it's not very intuitive, because on the oscilloscope we know that it's moving ahead. So as we move this way on the oscilloscope, we know that the signals are actually newer the further that they are across on the X scale. So for example, in this case, it would be more intuitive to actually come along and say, well, the current at this stage is actually newer, so therefore the current would lead the voltage. And because we're at 90 degrees, so we would say that the current leads the voltage because it's peak at 90 degrees. It's wrong, it's not how you do it, and I just want to make that very clear. So in this image, voltage leads the current by 90 degrees. Now in a circuit where the voltage and current are out of phase, it's a very interesting debate for saying that current and voltage can exist one without the other. Most people would tell you that you have to have a voltage to get a current. However, in resonance systems there can be zero voltage, which is 0 here, and have peak current. It's a very interesting phenomena. Resonance does some pretty crazy things. It's very interesting to study. The oscilloscope is just fantastic, and viewing over time the different relationships for things like voltage and current and stuff like that. It's just absolutely critical in getting a good grasp on what's going on. You can see here current, voltage, and the purple is power. It's marked as power consumed and then power returned. Now, I don't like the power consumed because effectively it's not true. It's misleading. Power delivered and power returned should be the correct terminology. You can see here anytime the current is of the opposite sign to the voltage. So for example, in this case we have positive voltage all the way up to here, while the current value is greater than 0. Now at this stage we have real power. This is real power, but it's coming out of your machine. It's being delivered from your machine back to the power supply. And the opposite is true here. So this is positive power being delivered from your power supply to your machine. And you can see the cycle keeps going. Now this is at 90 degrees, at a perfect 90 degrees. You use no power, and I'll show you that now. I have just a small calculator I've built. Now we're just going to use 7 as the volts and ampere. Phase shift in this case we're going to use 90 degrees. So if we calculate, active power is 0, so there's no active power in the circuit at all. Apparent power 49, 7 times 7 is 49. Reactive power is 49, that's volt ampere reactive, and the power factor is 0. Okay, so all the power is in the reactive component. Now if we were to change, and if we were to change the situation and say, right, at this stage our phase angle that we've measured is 180 degrees, things change drastically. And this is really, really interesting. Now the books don't tell you this. This is not something that's anywhere in the books. But the power factor ranges from -1 to 1. The books will tell you from 0 to 1, but it's wrong. The correct figures are -1 to 1. Okay, so active power is -49 watts. Apparent power is 49, that's volt amperes. And again, the power factor is -1 in this case. So very interesting. Time relative. So if we're looking in time, in this case, our current waveform is further ahead in time. If we were to look at either the peaks or the zero cross. So at the peak up here, our voltage peak here. So our current is further ahead in time, but it's said that the voltage would actually be leading the current. The voltage happens before the current happens.